Hello everyone, Mr. John here from Areteem Institute, where today we're going to be talking about the AMGM inequality as our Thursday tidbit. Here AM is arithmetic mean and GM is geometric mean. We'll review those a little bit and then see how they are related to each other with this pretty famous inequality. Getting started here. Arithmetic mean. This is your normal average. So if you know what the average of some numbers is, the arithmetic mean is kind of the same exact idea there. So you have the sum of all of those numbers, and then you are dividing by how many numbers there are in this case. So this is your kind of normal average. One thing I always like to draw our attention to for these is relating them to arithmetic sequences, right? So for a very simple example here, suppose we have kind of an arithmetic sequence 2, 8, 14, blah, 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 right? So we have those kind of things there. And what if we look at 2 and 14, right? If we look at 2 and 14, right, the arithmetic mean is going to be 8 in this case. So this is a nice way to see where, if we have an arithmetic sequence, our kind of average of the two numbers is right between. That is our arithmetic mean. Now, what about a geometric mean? Let's take a look at that too quick. So, for an arithmetic mean of the n numbers, we take the product of those numbers, and now instead of dividing by n, we take the nth root of those numbers. So arithmetic mean, we have sum and then division. Geometric mean, we have product and then a square root in this case. Drawing the parallel to the sequences again, let's suppose we have now a geometric sequence instead. So we have 2 times 4 is 8. Now if we're doing geometric sequence, our next term would be 32. And now notice 2 times 32 is 64. The square root, if we have two numbers, gives us 8. So we can draw this similar parallel here. This is where I like, you might have heard of arithmetic and geometric sequences, and now we can relate those to the arithmetic and geometric means. And that's a good way to start kind of thinking about where geometric mean comes from as a definition, and we can also use it with these kind of simple examples for understanding terms in those sequences as well. Let's look at one now where we do a calculation with 3 numbers. So, quick example here. If we are given 3 numbers, so we have A1 is 3, A2 is 6, and A3 is 12. Let's calculate the arithmetic mean and the geometric mean. So these are pretty straightforward to do, right? Arithmetic mean, we add up the 3 numbers. So 3 plus 6 plus 12. And so then we divide those 3 numbers by 3. So we have 3 plus 6 is 9 plus 12, 21. 21 divided by 3 is 7. So our arithmetic mean in this case is 7. Similarly, we have a calculation for the geometric mean. Here we're taking the cubed root of 3 numbers. And again, we have 3 times 6 times 12 in this case. Now, just to kind of make this a little bit easier on us, note 3 times 12 is 36. 36 is 6 squared. So actually 3 times 6 times 12 is 6 cubed, because we have 36 times 6. Cubed root of that is, of course, 6. So in this example, we have the arithmetic mean of the 3 numbers is 7. The geometric mean of those 3 numbers is 6. Of course, these numbers don't need to be nice, right? We might not have a perfect cube. We might not have integers for the arithmetic mean as well. But here we have some nice numbers in this case. And we notice that the arithmetic mean gave us a bigger number than the geometric mean. And that's actually going to be pretty much the case for positive numbers at least. And that gets us to the AMGM inequality, right? AM, arithmetic mean, GM, geometric mean. So for non-negative numbers, A1, A2, all the way up to AN, we have the arithmetic mean, right? So this is written out in symbols here, but you might as well just kind of remember it as a shortcut. So we have our arithmetic mean on this side. So that is our AM portion of the inequality. And this is greater than or equal to GM, greater than or equal to the square root of the product of those numbers there. All right, we need to make sure we have non-negative numbers in this case. And we actually have a condition for equality. So you can actually tell where this stuff happens, and it's going to happen if all of the numbers are the same. The only way the kind of arithmetic mean is equal to the geometric mean is all of the numbers are equal here. So there's lots of applications you can do with this, but we'll take a look at one example of this today. So suppose x, y, and z are positive real numbers with 2x plus 8y, 2x plus y plus z is 8. What is the maximum value of x squared, y, z? Now, what should we kind of notice when we look at some stuff here? We have 2x, we have x squared. We have y and y, z and z. So we can look here at the four numbers. Our idea here is to look at four numbers. One of them is, of course, repeated. So we have x because we have 2x or x squared. We have y and we have z in this case. Now, it's different because we maybe have variables and stuff here, but can we look at the arithmetic mean and the geometric mean? Well, of course. So what is the arithmetic mean in this case? The arithmetic mean is the sum of these numbers, so x plus y plus z, so 2x plus y plus z, divided by 4. So this is divided by 4, is our arithmetic mean here. Now, before we write out the geometric mean, notice that this is actually something we can calculate, right? One of the motivations here for x, y, z was that now the problem gives us the sum. We are told 2x plus y plus z is 8. So if we write this out then, 2x plus y plus z, this is 8 divided by 4. So we actually know then in this case that the arithmetic mean is equal to 2. So this is what we have here in this case. Now, what about the geometric mean? Right? I think you probably see where this is going for now. Right? The geometric mean is the fourth root. So we have the fourth root of the product of these four. Well, wait a second. The product of these four things is x squared y z. So this is exactly that value we're looking for in our question. We have the maximum value of this thing there as well. Now, remember the inequality here, right? AMGM inequality tells us that the arithmetic mean is always greater than or equal to the geometric mean. So we actually have here that the fourth root of x squared yz is less than or equal to 2. So we actually have then, rewriting this and putting to the fourth power of both sides, x squared yz is less than or equal to 2 to the fourth power, which is of course then 16. So we have this as our maximum value in this problem. So the maximum value here is 16 in this case. We actually can do a little bit more, right? If you're curious about this or want to kind of see about this as well, right? This occurs When, right, when does this happen? Well, it happens when x equals y equals z, right? X equals y equals z. All four values have to be the same. And in this case, that's pretty easy to see. The four values are the same, right? Their sum is 8. So the four values all have to equal 2 there. That's not actually needed for our problem, but it actually is true. We can use this AMGM inequality to tell us, okay, the maximum value is 16, and if you're curious, that happens when all x, y, and z are 2 in this case. There's a lot of more confusing examples where you have to do some manipulations with these things, but even in simple cases, it's a pretty powerful tool for dealing with maximizing things, minimizing things, and some optimizations questions that way as well. That'll do it for this week's Thursday Tidbit though, so please check back each Thursday for a new math tidbit in 2021. Right, if you like this video, if you have other examples to share, please like it below, subscribe below, let us know in the comments if you have suggestions for further videos, follow-up questions, etc. And check out ziml.areteem.org for more practice as well. Goodbye, everyone.